Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into a classic coding problem.
Yeah.
One that can really trip you up in a technical interview if you're not prepared.
Yeah, definitely.
We're talking about converting fractions to decimals.
Right.
You know, like turning 1/2 into 0.5.
It sounds simple,
Right.
but it's a little more complicated than that.
It is.
What happens when you have a fraction like 1/3?
All right. You get 0.3333333 going on forever.
Exactly.
Those pesky repeating decimals.
Yeah, and if you're trying to code this conversion, you can't just let your program run infinitely just spitting out threes.
Right.
That's where things get a little bit interesting.
Yeah.
We need a good way to handle those repeating decimals and represent them correctly.
So what's our first hurdle here? How do we even begin to think about this problem, like from a coding perspective?
Well, the first thing we have to do is clearly define the problem.
Okay.
So we're given any fraction,
Okay.
meaning a numerator and a denominator. And our task is to output its decimal representation.
Right.
The challenge is to represent those repeating decimals accurately,
Yep.
like showing 1/3 as 0.3 with the parentheses indicating repetition.
So no rounding off allowed.
Exactly.
We need that precision.
Yeah, especially if we're dealing with anything where accuracy is super critical, like financial calculations or scientific simulations.
Right.
Rounding errors can cause all sorts of problems there.
For sure.
Now I know what you're thinking.
What am I thinking?
You're thinking, couldn't we just keep dividing the numerator by the denominator and look for a repeating pattern?
Well, yeah, that's kind of what I was thinking.
Yeah.
Like a brute force approach.
Yeah.
But wouldn't that get really messy and inefficient? Especially if the repeating block is long?
You hit the nail on the head. That brute force approach has a couple of big drawbacks.
Okay.
First, how would you know for sure that a pattern is actually repeating?
Right.
You could end up checking a ton of decimal places and still be unsure.
Yeah.
And second, it's very inefficient, especially for fractions with those longer repeating blocks.
Right.
You could end up in an almost infinite loop, and that's really bad in coding.
Yeah. That's not good.
So,
brute force is out.
yeah,
We need a more elegant solution.
right.
Something that can detect those repeating patterns efficiently and represent them correctly.
Yeah.
Any hints on where we might find such a solution?
Well, think about it this way. As we're performing that long division, is there anything that might signal to us that we're about to enter a repeating cycle?
That's a good question.
Yeah.
Let me see. We get the integer part of the decimal easily enough.
Right.
But then as we start calculating the digits after the decimal point, we're performing divisions, and each division gives us a new a remainder. Could
Yeah.
the remainder be the key here?
You're on the right track. The remainders are crucial.
Okay.
Now, how can we use those remainders to detect a repeating cycle?
Maybe if we see the same remainder more than once during the division process,
Yeah.
wouldn't that mean we're about to repeat the same sequence of calculations, leading to the same digits in the result?
Bingo. That's the insight we need.
Okay.
If we encounter the same remainder again, it's a clear signal that we're about to enter that repeating cycle.
Okay, that makes sense. But how do we keep track of the remainders we've already seen in a way that allows us to quickly check for those repetitions?
Okay.
I can't imagine manually writing down each remainder as we go.
Yeah, no, that wouldn't be very efficient.
Not at all.
That's where a really cool data structure comes in.
Okay.
It's called a hash map
Okay.
or a dictionary, depending on which programming language you're using.
Okay, I've heard of hash maps, but remind me what they are and why they're so useful in this situation.
Yeah, so a hash map is essentially a lookup table where we can store key value pairs.
Okay.
And the cool thing about a hash map is that it allows us to access any value almost instantly if we know its corresponding key.
Got it.
So in our case, we can use the remainders as keys
And store the position of that remainder in the decimal as the value.
yes.
So if we get a remainder of 3 while calculating the second digit after the decimal point, we'd store 3 as the key and 2 as the value in our hash map.
Exactly. And as we continue with that long division, we can quickly check if each new remainder already exists as a key in our hash map.
Right.
If it does, boom, we know we've hit a repeating cycle and we know where that cycle starts.
This is brilliant. It's like a detective using fingerprints to catch a repeat offender.
It is.
But I think we need to illustrate this with an actual example
Yeah.
to really see it in action. What do you think?
I completely agree. An example will make everything crystal clear.
Okay.
Let's tackle the classic 1/7 conversion.
Perfect. I've always wondered how to accurately represent 1/7 as a decimal.
Okay.
Let's break it down step by step and see how this hash map trick helps us crack the code.
Great. So first things first, what's the integer part of the decimal representation of 1/7?
Well, 1 divided by 7 is 0, with a remainder of 1.
Yeah.
So our decimal starts with 0.
Excellent. Now we move on to the decimal part, building it digit by digit. Where do we begin?
We take our remainder, which is 1, multiply it by 10 to get 10, and then divide that by 7. It
Okay.
gives us 1 as the first digit after the decimal point and a new remainder of 3.
Perfect. Now this is where our hash map comes into play.
Yeah.
What do we do with that remainder of 3?
We store it in our hash map as a key, and its value will be its position in the decimal, which is 1, since it's the first digit after the decimal point.
Exactly. So far our decimal is 1.1, and our hash map looks like this. 3, 1. Now what's our next step?
We take our new remainder, 3, multiply it by 10 to get 30, and then divide by 7.
Okay.
That gives us 4 as the next digit in our decimal. And what's the crucial piece of information we need to calculate and check?
Yes. What is it?
The remainder,
Yes.
30 divided by 7, gives us 4 with a remainder of 2.
Okay.
And since this is a new remainder, we add it to our hash map along with its position, which is 2.
You got it. Our decimal now reads 0.14, and our hash map has grown to 3.122.
Okay.
Let's see what happens as we continue this process. I have a feeling things are about to get interesting.
I'm ready. Let's see if we can catch that repeating pattern in action. All right, so we've got 0.14 as our decimal so far, and our hash map is 3.12, keeping track of those remainders.
Right.
What's next?
We just continue the process. So take that remainder of 2, multiply it by 10 to get 20, and divide by 7.
Okay, 20 divided by 7 gives us 2 as the next digit with a remainder of 6, another new remainder.
Yep.
To add to our hash map, it'll be 3.122636. Since 6 is the third digit after the decimal, so our decimal is now 0.142.
Perfect. Notice how we're basically simulating that long division process.
Right.
But with that added power of the hash map
Right.
to keep track of the remainders.
Exactly.
So what comes next?
Let's see. We take the remainder 6, multiply by 10 to get 60, and divide by 7.
Okay.
So that gives us 8 as the next digit and a remainder of 4. Our hash map now looks like this. 1, 2, 2, 6, 3, 4, 4.
Okay.
The decimal's growing 0.1428.
Keep going. We're getting close.
Okay, feeling the momentum here. Remainder of 4 times 10 is 40. Divided by 7 is 5 with a remainder of 5.
Okay.
Add that to our hash map. 3, 1, 2, 2, 6, 3, 4, 4, 5.
All right.
Our decimal is now 0.14285.
Now things are about to get really interesting. We have a remainder of 5.
Uh-huh.
What do we do?
Multiply by 10, which gives us 50, and then divide by 7, that's 7, with a remainder of 1. Wait a second.
What is it?
Remainder of 1. We've seen that before.
Exactly. We encountered a remainder of 1 at the very beginning.
Right.
Before we even started calculating the decimal digits.
So this means we're about to start repeating the same sequence of calculations, right?
Precisely. And our hash map tells us exactly where this repetition begins.
Oh, okay.
Look back at our hash map. What's the value associated with the key 1?
It's 0.
Yeah.
That's the position where we first encountered the remainder of 1.
Which means the repeating block in our decimal representation starts right from the first digit after the decimal point.
So the decimal representation of 17 is RZA.142857. We've cracked the code.
We did it.
I have to admit, that was pretty satisfying.
It's elegant, isn't it?
It is.
A simple but powerful technique.
Yeah.
Using a hash map to detect and represent those repeating decimals.
Absolutely.
Yeah.
But I'm curious, what's the efficiency of this algorithm like, in terms of time and space complexity?
That's a great question. Let's analyze it. In the worst case scenario, the repeating block could be as long as the denominator -1.
Like in our example with 17, where the repeating block has 6 digits and the denominator is 7.
Right. So in the worst case, we'd have to perform the division and store up to the denominator -1 remainders in our hash map.
Okay.
This means that both the time and space complexity would be roughly proportional to the denominator.
So if we had a fraction with a huge denominator, it could potentially take a bit longer to compute and use more memory.
That's true, however. In practical applications, the denominators we encounter are rarely that large, and the repeating blocks aren't usually that long.
Right.
This method is generally very efficient for handling the vast majority of fractions.
That makes sense.
Yeah.
I'm also thinking this whole idea of using a hash map to detect repeating patterns, isn't that a broader concept in computer science?
It absolutely is. This technique falls under a concept called cycle detection, which has applications far beyond just converting fractions to decimals.
Okay, that's ringing a bell, cycle detection. I've heard that term before. But can you give us some examples of where else this concept pops up in the world of programming?
Certainly imagine you're dealing with a linked list, a data structure where elements are linked together in a chain now. Sometimes due to programming errors or specific algorithms, this linked list can end up having a cycle, meaning it loops back on itself.
Ah, I see where you're going with this. We could use a hash map to keep track of the nodes we've visited as we traverse the linked list, and if we encounter a node that's already in our hash map,
We know we've detected a cycle. It's the same principle as our fraction to decimal conversion, just applied to a different data structure.
that's fascinating. So this technique is surprisingly versatile.
It is. Cycle detection is a fundamental concept with applications in various areas, including graph algorithms, cryptography, and even detecting patterns in data streams.
This has been a truly illuminating deep dive. It's amazing how a seemingly simple problem, like converting fractions to decimals, can lead us to such powerful and widely applicable concepts in computer science.
I agree, and it highlights the beauty of algorithmic thinking, finding elegant solutions to seemingly complex problems.
Well said. So any final thoughts or challenges for our listeners before we wrap up this deep dive?
Yeah.
I think our listeners are really going to walk away from this episode with a much deeper appreciation for fractions and decimals and the clever algorithms that kind of bridge the gap between them.
Yeah, definitely. I hope so. It's a great example of how, like, a seemingly basic problem can unlock a whole world of fascinating computer science concepts.
Speaking of challenges, any final brain teasers for our listeners to ponder something to really stretch their coding muscles?
Here's one that builds on what we've been discussing. How would you adapt this hash map algorithm to handle irrational numbers like pi?
Ooh, that's a good one. Irrational numbers have those infinite non-repeating decimal expansions, so our current method wouldn't quite work.
Exactly. It requires a different approach altogether. It might involve looking at continued fractions or other advanced techniques for representing those irrational numbers.
That's definitely something for our more ambitious listeners to explore. I'm already feeling inspired to do some research myself.
Yeah, and that's what it's all about, sparking that curiosity and encouraging that continuous learning.
Well said. I think we've given our listeners plenty to chew on today. It's been a fantastic deep dive into the world of fractions, decimals, and the elegant algorithms that connect them.
I've enjoyed it too. Always fun to unravel these coding mysteries.
Thanks for joining us on AI.Code.Cast. Remember to subscribe for more deep dives into the fascinating world of algorithms and problem solving.
Until next time, keep coding, keep learning, and keep those hash maps handy.